vAXIom platform. 5 easy steps to build your system on chip. During this short tutorial, we will show how to set up system on chip on FPGA in one day using vAXIom platform automatically generated synthesis and simulation environment. A sample synthesis environment is shown here. It consists of a number of modules. The main module is vAXI module, which is a bridge between AXI interconnect and user logic, which can be easily connected on the right side of vXI, which is completely customized and can contain a different number of ports, as we will see later on. AXI interconnect has a number of additional connections, for example, one to the ARM processor, and another special connection is automatically generated toward microblaze debug module, allowing access to the entire address space of the user through JTAG connection and XMD debug tool, XMD terminal. Through the XMD terminal, we can send commands to our address space, like read and write commands, and also the vAXIom platform will automatically generate a BEAST program for the customized address space. We'll generate a sample synthesizable module and we'll burn it into Z-board containing Zynq device. In addition, the vAXIom platform will generate around the synthesizable top additional test bench environment, and where ARM processor will be replaced by a special master module which will execute commands written in a simple commands file, and the commands will be translated to AXI transactions towards the memory address space of the user. The user can later on add additional commands here and add additional modules, as we discussed before, and in this way the user can continue building the project from the initial infrastructure of simulation and synthesizable onboard environments that the vAXIom platform provides. So the design flow is as follows. At the first step, the user will customize and generate vAXIom modules along with the synthesis and simulation environment. Then we'll just run synthesis and generate the bitstream. We'll burn the bitstream into the Z-board, and then we can immediately talk to entire address space that exists inside that we will define, and it will be accessible through the XMD console of Xilinx and through the ARM. Once this works, we have two environments, simulative and the synthesis with onboard one, which will serve as the infrastructure for the further development, gradually adding more modules to our top module. So now let's do the step 1 and customize the vAXI module. I'm running now vAXI user interface. At the first stage here we can define different clocks that exist in the system, and we can define the clock rates for these signals, for these clocks. And then on the next stage we will define the target device. We can target FPGA or ASIC, any device of Xilinx, which also do not contain ARM processor, speed grade, and so on. All this information will be employed for enhancement of the reliability, especially in the case when vAXI will be connected to multiple clock domains. On the next stage, we will define the left side of vAXI module, where we can define any standard of AXI4, including AXI4 or AXI4 Lite, any address bus, data bus widths supported by the standard, and so on. On the next stage, we can define the right side, the user side of the vAXI module. For example, we can add multiple ports. We can manage these ports. For each port, we can give a name of the port. For example, my test port. We can choose the target clock. It could be a different clock from the AXI clock. And then we have a choice to add here additional interfaces. For example, buffer streaming interfaces, where we can choose a different width, and different protocols, and we immediately see the protocols on the left side of the user interface. Same for the right streaming. In addition to the streaming interfaces, we have the register and RAM interfaces. When the RAM will be placed inside vXI, so I'm defining here address space for the RAM. When the Xilinx RAM will be automatically generated along with its NGCs inside vXI module. I can choose different sizes. Okay, so I now generated a RAM module inside vAXI, and one connection is provided to the user. I can do the same with a register bank, and here I added 32-bit register. The register can be either internal or external, and in addition we have a special SBUS interface which allows external connections. Once we defined our ports, we can generate all the environments. I just need to provide the name for the wrapper module, and I should say where I want to save it, and now I can generate the entire thing. So first, vXI will generate the memories, will generate all the NGC files if we have memories inside, and then it will run vivado and will generate vivado environment for the synthesis. Now vivado environment is set up. Okay, and now we can take a look and see what was generated. So here we see the project of the user interface, which can be opened anytime and recustomized. We can see the synthesis stop, which will burn into the Z board. Here we can see the vAXI wrapper, and we can identify the myTest port RAM interface and register bank interface. We can see that the test bench was automatically generated, and the test environment for modules in with the example commands file were also generated. In addition, all the memories with all the NGC files were automatically generated. And of course, test and script directory were generated, where the synthesis folder contains the vivado project, which we can open, and we can see the script that was generated for the testing on the board, writing the data to the memory and reading the data from the memory, and then doing the same for the register bank. We can see that vivado is automatically set up to look at the synthesis stop. We can see here the AXI interconnect with all the components inside, and we can see the AXI vAXI modules that we generate. So what is left is only to generate bitstream and burn into the Z board that we have just prepared. So now let's run the synthesis. To save the movie time, we have just kept the synthesis time of vivado, and now our bit file is ready, so we can burn it into the board. So I will run impact. My Z board is already connected. Here we can see Zynq processor and the FPGA side of the Zynq. So I will assign my bitstream file from which was automatically generated by Vivado, and now I can burn it. And we are set up with our functional SoC. Now, as we already mentioned, vAXIom platform generated a special bistro script for their testing of the user environment. So first we will write the data to the board, and then we will read it back from the memory. And we had also a register bank interface, so we'll do the same for the register bank, and then we will just play with the LEDs. So in order to do this, I'm opening the command prompt, and I will go to the script location, and here I will just run the sample script. So the script will turn on the XMD terminal, and then we'll issue all the commands and will return errors in case of the error. And now you can see that the memory was written and the read from without errors. Same for the register bank. And now if you were me, you could see the blinking on the board. Congratulations! Your first system on chip is fully functional on a real board. Now you can keep adding your RTL blocks to the synthesis and simulation environment, performing software-hardware integration in parallel. Good luck!